We're going to take the ideas that we've delved in with differential equations. We've done a little bit of differential equations along the way. We've talked about slope fields, and we're going to marry those two things together. At the end of this slideshow, I will show you an example of a true AP question that we've seen in the past that deals with these two different things. Okay, so you should be able to use initial conditions to find a particular solution of a differential equation. So again, in general terms, a differential equation takes a derivative and says, what's the original function that generates this derivative? It seems like an integral, and it kind of is an integral, but it's not really. I mean, you end up using integrals in the process. And then the other thing today is you should be able to drive a stick shift car. Who can? None of you can drive a stick shift?
I could try. I've done it before, but I wouldn't say I'm confident in doing that.
Okay. A lot of grinding?
No.
A lot of jerking?
Yes.
Yeah, that happens. Yeah, great. Okay, here we go. We're not going to spend a lot of time on this slide because I've talked about this already. We talked about a family of solutions and going from a family of solutions to a particular solution. The family of solutions would include that plus C term. The specific solution has no plus C term. So we go for an infinite number of possible answers down to one and only one answer that we represented in some of those pictures. The only reason I'm talking about this is this scenario pops up every once in a while, and that is they want you to confirm that these two functions satisfy this differential equation. Okay. They're saying y prime minus y is equal to 0. Okay. And all you have to do is confirm it. So in order to confirm it, I need to know what y prime is. I need to know what y double prime is. So we'll do the sign one first, or I'll just draw on the board. There we go. Okay? Derivative of sine is cosine. The derivative of cosine is negative sine. You take those values, plug into the function. Y double prime minus y is negative sine minus sine, which is negative 2 sine. That is not equal to 0, therefore it doesn't work. And in true instructional process fandom, the first one doesn't work. What can you guess about the second one? It's gonna work, yeah. By the way, what's C? A constant. What's C plus C? C times C? C squared. C divided by C? C. Okay, good. You all sound Spanish. Bien. Gracias. What's the derivative of C e to the x? What's the derivative of e to the x? E to the x. What's the c do? Nothing. Absolutely nothing. So what's the derivative of c e to the x? C e to the x. And what's the derivative of that? C e to the x. What's the ninth derivative of c e to the x? You guys are so good at pattern recognition. I couldn't be prouder. Plug and chug. C e to the x minus c e to the x is 0. It doesn't matter what c is. They're going to cancel out. So yes, that one works. Hot diggity. It follows the pattern. Boring. Let's do instead a differential equation. Okay? Today, however, we're going to throw a new twist in. You'll see at the top, it says solving separable differential equations. Okay, I cannot stress this enough. You must separate the differentials. And you're saying to yourself, self, what is he talking about? This dy and the dx are called differentials. We know dy dx as the derivative. So the derivative of y with respect to x is 2x cubed minus 3x. Going backwards, we would take an integral. Okay? And I kept hyping on you that you always need this dx. You always need. Well, this is where it rears its ugly head. When it says separate the differentials, it means put the dy on one side, Put the dx on the other side. Ideally, the dx is with the x's. The dy is with the y's. I don't have a y, so I'll just leave that alone. So I picked a fairly easy example. I'm going to multiply both sides by dx, and I get that. Okay? I've successfully separated the differentials. Now you're saying to yourself, Self, that doesn't seem that important. I'll show you why at the end of the slideshow, why it is so important. Well, what does that differential do? We've kind of, and I don't know if I don't remember if I talked about this, but we've always had that dx for every time we take an integral. You know, what's the integral of x squared dx? What's the integral of 2x cubed minus 3x dx? Why is the dx there? In this class, the dx represents the variable that we're talking about. Okay, so on the right-hand side, we're taking, well, you can guess where we're going here. We're going to take an integral, and my variable is x. On the left-hand side, I'm going to take an integral, but my variable is y. Okay, so let's do the easy one first. What's the integral of the right-hand side of that equation? Is it on the slideshow? Oh yeah, okay, so nobody was even innovative enough to just read my own slideshow to me?
I'll read it, but
Okay, read it,
I
Mom.
feel like I'm cheating.
I understand. We still love you.
1/2 x to the 4th minus 3/2 x squared plus.
Beautiful. Okay, so simple integral. The left-hand side, however, my variable is y. Therefore, when I take the integral of dy, that's the same thing as 1 dy, I'm going to get y. Well, that's where we want to be. Now I've taken it backwards to get the function that gave me that derivative. Okay? This is something we've done ad nauseum. The only difference now is I'm throwing that separable differential in there. Split up the dy and the dx. You have to. Okay. Again, general solution. We cannot solve for the particular solution because I don't have enough information. I don't know what point you're talking about, so there's our general term. Questions? Pretty easy, yes? Lily, why do you look horror-struck? You're good? So let's make it more interesting, shall we? Oh, by the way, yeah, in big red, you must separate differentials, right? In case you didn't see that, you must, again, separate the, okay, do you see it there? Good, I'm making it flash. It's really important. Separate the differentials. Are we getting this?
Yeah.
Good, can I stop doing this?
Yeah.
Good, let's move on to the next one then. We did the slope field for this already, if you'll recall. What shape did we get? Circle. Okay. So now we do the math. Step 1, separate the differentials. I'm going to multiply both sides by dx, and I'm going to move the y over to the left. So I get this. Adrian, let's pick on you. What do you want to do with that minus sign? Do you want to leave it here, or you want me to take it with the y? Either one is correct. It's entirely up to you.
Let's move it over to the other side.
Take it with the y. Okay. Multiply both sides by dx, multiply both sides by negative y, and we get that. Take the integral of both sides. Yep. This isn't in my slideshow, is it? Emma?
Well, I just had a question.
Sure.
Anytime there's like both variables, do you always have to get them on the side with that differential?
99% of the time, 100% of the time, that's your goal. Whether or not you can do that is a little tricky. For our purposes, yes. You should be able to move the y's and the dy to one side, the x's and the dx's to the other side. It just might be uglier.
And then if it's like one that we just did, you only have to worry about the x's staying on that side.
Correct. Okay. How are we doing so far? Good. Faith, what's the integral of negative y? dy.
So negative 1/2 y squared.
Beautiful. Oh, you forgot something, Faith? Plus C, good. So if you can think about where I'm going here, I'm going to get a plus C on the left. I'm also going to get a plus C on the right. Then I've got to move one C to the other side, and I'm going to end up with C. We're not going to bother. We're going to save ourselves some hassles, and we'll just agree to do the same thing. We're going to agree to just put the C on the X term. So yeah, Faith, you're correct. There should be a plus C there, but we're just going to say, no, I'm smarter than that. I'm not going to bother. All right, Faith, what's the integral of X?
1/2 x.
Beautiful. We have an initial condition here. I know that the curve passes through the point 1, 1. So I'm going to plug and chug. Negative 1/2 equals 1/2 plus C. Therefore, C equals? Thank you. I was just about to say you're kidding, right? Therefore, we get negative 1/2 y squared plus, nope, not plus, minus, equals, equals 1/2 x squared minus 1. So you're saying to yourself, self, that doesn't look like a circle, but you're all fairly bright and can realize that if I solve that and manipulate it a little bit, I can actually get a circle equation. If I move the 1 to the other side, I'll do that in a different color, I get 1 equals 1/2 x squared plus 1/2 y squared. Multiply everything by 2. I get 2 equals x squared plus y squared. And sure enough, you know that is a circle. With its center at? Where's the center of that circle? You can't hear me, right? No. The origin, correct. What's the radius of that circle? Square root of 2. Very good. However, on most calculus problems, instead of solving it like I did into a nice pretty form like a circle, they're going to ask you to solve for y. Okay. So this isn't typical. I'll put it in a weird shape there. I'll get rid of this and do what we would actually do on a problem. And that would be to do y squared is equal to negative x squared plus 2. And therefore y is equal to plus or minus the square root of negative x squared plus 2. Are we done, boys? You sure? There's a lot of giggling coming over there, from over there. I mean, if it's that funny, you could share the joke with all of us, or you could stop snickering like a bunch of children. Which one's it going to be? 2. Good choice. Plus or minus, y? Square root. But it can't be plus or minus. It just has to be plus. And this is a common issue. Why is it just plus? And the answer to this is so obvious you don't notice it. Y is positive. And since y is positive, we only take the positive part of that. That's a little meatier differential equation. Questions so far? We're good? So this is from the year 2006, long time ago. Were you guys even born yet? Yeah, okay, just checking. What year were you born? 3 or 4?
4.
I literally have shoes older than you guys. So this is one of the free response questions from the 2006 AP test. Two parts to it. First part is a slope field. To satisfy part A, all you got to do is draw a bunch of dashes like we did in class the other day. The second part is where things get a little bit ugly. But you'll also see that that part B is identical to the problem I just solved. They give you a function. They ask you to find the differential equation. They give you some starting information. Okay, so negative 1, 1 is going through the curve. We're not going to do the problem. I just wanted to show you what this looks like. Here's the answer key. So they want you to draw a little sketch of what the slope field looks like, draw some dashes, and then solve this. The thing I wanted to point out, and the reason I included this in the slideshow, is that little message. This also warrants a little bit of explanation. On the actual AP test, you will see 6 of those problems. 6 free response questions. 2 of them are calculator, 4 of them are non-calculator. They are all worth 9 points. Every AP free response question is worth 9 points. That constitutes half of the test. The other half of the test is all multiple choice. Part of the multiple choice is calculator, part of the multiple choice is non-calculator. So, knowing that that's worth 9 points, you get 2 points for drawing a bunch of dashes. That's pretty reasonable. And then this whole solution of the differential equation is worth 6 points. You'll notice the note. If you don't separate the differentials, they're going to give you 0 on it. Which is why you need to be sure to separate the differentials. Question?
I just have a question about like the actual like slope field. Are they like super strict about like if you were to draw a slope field, are they super strict about like the angles?
No, because notice they say sign of the slope at each point, relative steepness of the slope lines. In other words, as I move up from this point upwards, it has to tilt more. So that one's going to be obviously horizontal. But as long as it's getting more steep, you're good to go. As long as you move to the right and it gets less steep, you're good to go. Yeah, you don't have to exactly draw a little dash with a slope of 3 or whatever it is.
Okay.
Okay, good. We're done. There's a bunch of students in the parking lot making a slope field. We could do this later if the weather gets nicer. That'd be fun, yeah. Yeah. Who's in? Anybody? Okay. Okay. Not today, though.